So first off, what is Eclipse? So Eclipse is building scalable modular application-specific rollups using the Solana VM. So what this means is that currently for most L1 chains, all application devs share the same chain. And so like in times where there's like a lot of demand for the chain, it can get really contested. Gas fees can get really high. In the case of Solana, sometimes like people spam like thousands or tens of thousands of transactions a second, which really bottlenecks the network. So what we're doing in Eclipse is essentially building rollups for every specific app. So every app will have its own dedicated app chain that all settles to a single Eclipse settlement chain. And app chains can choose what data availability providers to actually store their blocks in. And Celestia is one of the main data availability providers that we are supporting in our initial DevNet releases that are targeting early next year. So what is IBC? So IBC stands for the Inner Blockchain Protocol, and it's essentially a protocol for very basically sending messages across chains. Why might you want to do this? Well, the easiest example is if you want to bridge assets across chains or do trades across chains, you can like take your value from one chain, move it to another chain. We need like some sort of secure way to make sure that those messages are sent across correctly, that people aren't doing things like double spend transactions. And so IBC provides a framework to enable this to happen. So here are some of the key components of IBC. So when we talk about IBC, typically we're talking about two chains that are communicating with each other. And so both of the chains need to have some things like built on top of them. They need the core protocol of IBC, which is just like, which I'll talk about in the upcoming slide. This is the actual like language of the messages that need to be sent like across chain, so that both chains and the relayers in the middle will be able to understand the messages. Both chains need a client for the other chain. Talk about this a little bit more. Basically what this means is that every chain should be able to read the state from the other chain and verify that that state that it received is actually correct. The third part is, so for apps that are building on each chain, they need to like integrate into what they're called modules. These modules sort of plug into the core IBC logic and are able to like make IBC messages. And essentially when we talk about sending messages through IBC, what we're really talking about are apps that write modules, and these modules talk to each other. And finally, there's a relayer that needs to sit in between these two chains. This is like an off-chain program that listens to messages on both chains and then ferries messages across to the opposite chain whenever it sees like a message on like a sending chain. So I'm going to walk through the IBC core protocol to give you a sense of what this looks like. So ICS2, as I mentioned, is the series of official IBC standards that designate like how the protocol works. So ICS2 talks about clients, and usually these are light clients because it's sort of infeasible to run like an actual full client on chain typically. So this client must do two main things. The first thing is actually being able to parse the other chain's data. So given like this blob of binary data, the client must be able to like deserialize this based on whatever format it's stored in. And then the other thing is that it must be able to verify that this state has consensus. So all Cosmos SDK chains use Tendermint as the built-in consensus mechanism. So since IBC was designed with Cosmos in mind, it has built-in support for Tendermint. If you are going to connect to a chain that doesn't use Tendermint, say Ethereum, then you would need to write logic that like understands for the signatures of the validators, maybe like the structure of like the Merkle tree that the data is stored in, and be able to sort of verify that all those signatures were signed correctly, that they were as you expected, and that the data is actually present in this like a group created on like big state. So now that we have light clients, we can now be able to like start creating connections between two different chains. So a connection just represents like an open link between two chains. So every connection needs to use a specific client so that the connection is able to like understand what the other chain is saying and be able to like establish this handshake to start a connection. Of course, like the same client can be used with multiple connections. So if we are connecting to multiple Cosmos SDK chains, well, the protocols that they speak are exactly the same. So we can reuse the same like Cosmos SDK Tendermint client to talk to both of the chains. So here is a diagram of what starting a connection looks like. So as you can see here, there's two chains and they want to communicate across each other. So a connection is initiated when something on chain A I'm just referring to as like the starting chain, something on chain A sends a con init message to the IBC core module. It just says like, okay, I want to start a connection with this other chain using this client. If that con init is successful, then in the middle here, what it isn't labeled is like this whole section is what the relayer is doing. So the relayer is listening to messages on chain A. It sees a con init that was successful and then says, okay, chain A wants to talk to chain B. I'm going to send a con open try message on behalf of chain A to chain B. If that is successful, it'll read the chain B state. And it's like, okay, chain B accepted that connection. I'm going to tell chain A, con open act. We're going to act the fact that chain B opened the connection. And once that's successful, send the con open confirm. So if you're familiar with TCP, for instance, this looks pretty similar to a SYN-SYNAC ACK handshake, and effectively serves the same purpose. It's just telling both chains, making sure they both have like the correct state of both chains in mind, and making sure that both chains are aware that this connection is open. Next, so if you've been paying attention, I actually skipped from ICS3 to ICS5. I think this is just because the way they're organized is a little bit weird. So ICS5 talks about ports. So in IBC, as I mentioned, there are modules which represent apps. Modules end up talking to each other. These could be things like smart contracts or Cosmos modules. And modules bind to a port to identify themselves to IBC. And this works like sort of similar to ports on your local machine. A module can actually bind to multiple ports, but for our purposes, this isn't super important. And so once a module is bound to a port, it can establish channels of communication between a port on like their chain and then like a port on like a remote chain that they've already connected to. So channels have like a few different properties. They can be unidirectional versus bidirectional. That just means messages are going one way or messages can go both ways. And then they can be ordered versus unordered. This just means like packets must arrive in order versus packets can arrive out of order, but then like something has to sort of like wait until all the packets arrive in order afterwards. So here's a diagram of channel establishment. If you saw the last diagram, this is basically exactly the same thing. It's just like one level up. So instead of establishing a channel, we're just establishing a connection. Otherwise, the messages roughly work the same way. So I'm not going to go into this too much again. And then channels can be torn down. This is pretty straightforward. One side says, I want to close the channel, and then it just gets relayed to the other chain using a relayer as well. So once channels are established, channels let you deliver packets back and forth. These packets, again, are very inspired by TCP. They contain a source port in channel, a destination port in channel, a sequence number saying like which packet number it is, and then the actual like binary blob of data that they have. So packet delivery is pretty straightforward. This is sort of the core of what the relayers do. So after connection is established and a channel established, the relayer's main job is to sort of ferry these packets over. So whenever it sees a send packet on any chain, it needs to take that and then send a corresponding receive packet onto the chain that it needs to be delivered to. And this is the primary way that data actually gets across between different chains. There's some timeout mechanisms on the packet itself. So if the packet doesn't get delivered for like 10 or 20 block heights, this is like configurable when you send the packet. Chain A can choose to time out that packet, and then that timeout also needs to be delivered over to the other chain. But yeah, so these are the basic building blocks that you need to send messages across IBC. There's a few other specs that I did not mention, but this is like these are the main components. So with these sort of like layers of building blocks, you're now like able to send packets across. One thing I do want to point out is that the relayers in the middle here are untrusted. So IBC security does not rely on the relayer here being trustworthy. The relayers can send whatever messages across between chains. So going back to the very beginning of this presentation, both chains have a light client for the other chain, and it's within these light clients that the validation of all the messages happens. So the security of IBC depends on the light client implementations of both chain B on chain A and chain A on chain B, like being correct. Because if the relayer is being malicious, the light client can just reject the message that the relayer tried to send across because it wasn't actually on chain A. So that's what the security of IBC kind of depends on, is the security of like these messages on chain. So what are some applications that you can use IBC for? So these apps are actually sort of like apps defined within like other spec numbers. So there are two categories that IBC is currently focusing on: cross-chain activity and transfers. So for cross-chain activity, there's this idea of interchain accounts. So you have an account on one like host chain, and then you can sort of maybe use the same private key or use like the same account address and use that same account on other chains. And except instead of having like local accounts on those chains, what you do is you just send IBC messages, and then that lets you interact on behalf of that account on the other chain. Cross-chain data queries is the idea of like being able to query information about a different chain. Say you're on Solana and you want to query Ethereum price data in a very cheap way. You can use ICS31 to sort of establish that. And then cross-chain transfers. So these are mostly named after the ERC number. So ICS20 is like the fungible token transfer. ICS721 is NFT transfer across chains. Cool. So I want to jump a little bit into IBC and Eclipse and some of its unique challenges there. So Eclipse, as I mentioned at the beginning, is a Solana VM, not a Cosmos SDK chain. So unfortunately, because we're not built on the Cosmos SDK, we don't get the IBC module for free. Like we can't really use the module because it's designed with Cosmos SDK in mind. So a lot of the initial work is just re-implementing the core protocol on Solana, which is written in Rust, and building that up. So that was like one of the first things that I was working on. And the second thing we need to do is build light client support. So for Eclipse on any Cosmos chain that we're trying to connect to, and for Cosmos chains on Eclipse. The latter mostly exists already, Cosmos chains on Eclipse, because there's an implementation in Rust. So the main big hassle is supporting Eclipses as a light client. So this means both understanding the data format of the Solana VM, as well as like verifying our sort of unique consensus mechanism. So we have sort of a unique settlement system given that we are a rollup. So that's been like a larger like a bit of work. And also an interesting point is that relayers also kind of need light client support. So the reason why relayers need a light client is that if it's trying to receive messages from both chains, it needs to be able to like look through the stream of messages, be able to filter out which ones are IBC messages, probably check that the messages are correct, because sometimes the relayer needs to deliver messages to another chain. And if that message was actually invalid, the relayer could be wasting gas sending a message to a different chain when like a real IBC message didn't actually get sent. So the relayer like does want to validate that the message is correct. So that's what I've been working on right now. And then another challenge is that Eclipse is an optimistic rollup. So I don't want to dive too deep into this, but an optimistic rollup essentially assumes that the transactions that are produced by the execution nodes is correct. But if there is a problem, if like someone realizes, oh, one of the transactions is incorrect, it can submit what's called a fault proof. And the protocol has a built-in way to deal with fault proofs. And if the fault proof is correct, the chain will be rolled back to a previous known correct state. So some other optimistic rollups include names like Optimism. I mean, this is a challenge for Eclipse as well, because like IBC kind of assumes that if the message got delivered across chain, that it was just successful. So there's not an easy way inside IBC to say like, oh, okay, this message was delivered, but now it's incorrect now. So can you drop it from the state? Like, so we have to like work around this a little bit. One way is actually to just work with IBC to like add this like into their spec as a way, like as like a part of their core protocol. That's one thing we're investigating. Another way might be, so like this challenge period could be like a week. So like one simple way is we allow people to start sending messages, but the messages don't get delivered to the receiving chain until that entire 1 week period has passed. Because after that 1 week, we know for sure that those transactions are final. This is straightforward to do, but UX-wise might not be the best for users because they have to wait this whole challenge period. A third way might be to deliver messages using a bridge instead of using IBC. So a bridge that like we're working on integrating is Hyperlane. So the way like Hyperlane could work is that it actually runs a full node of Eclipse, so that it can know for sure that the messages on IBC, the messages on Eclipse are correct. And so it doesn't actually need to wait the entire 2 weeks or 1 week before the message like gets sent over. So that's like another way. Maybe something like this could also be built into IBC if we work with updating the spec for this. And then there's some interesting challenges around like paying fees for relayers, because relayers have to pay gas to actually deliver these messages back and forth. So ICS29 is working on this. There's no chain right now that actually has support for this, but that's something that is interesting for Eclipse as well, given that we have these app-specific chains that might all have their own tokens. So this might be uniquely challenging for some relayers. Cool. And then, yeah, so that's mostly what we have. So, so in terms of Eclipse, so we're aiming for a definite launch early next year, sometime around January or February. So yeah, keep an eye out for that. And that's basically it. Yeah, I want to leave some time for questions if anyone had any.
Yeah, awesome. Thank you, Kevin. If anyone has questions, feel free to ask.
Yeah, you can also feel free to just send messages in the chat if you prefer that.
That too.
Kevin, I thought that was a great rundown and summary of IBC. In terms of the specific challenges for Eclipse, is it true that there aren't really light clients in Solana, and there isn't like a state root, for example? And like how do you get around that? Because doesn't IBC kind of like assume both of those things?
Right. I think there are, yeah, so I guess like, I believe that like Solana, it has like some unique challenges like you're mentioning. One like design that we are pursuing for Eclipse is like having this modular chain where the data availability is separate from the like execution part of Solana. And so like since we are settling to say Celestia, we have like some flexibility over how we represent the state. So we do plan on like having a Merkle tree to represent both the on-chain state as well as like some off-chain IBC related like message like logs that we don't actually want to like store on chain permanently because they're expensive. So yeah, we're still like working out the exact details of like what the actual data format on Celestia will look like, but we have some flexibility over like adjusting this, and then within the light clients that we build for the Cosmos chains as well as the relayer, we can have it know about like the specific Eclipse data structure so that it can actually parse these trees. But yeah, Solana doesn't give us some of this stuff like for free. Another challenge that Solana has is that it doesn't actually store all of its history in state, like similar to Ethereum, where like you can sort of retrieve anything from any time in the past. Like Solana doesn't have that as well. So that's also something that we have to work with too, because IBC might want to request messages maybe like 5 or 10 blocks in the past.
Got it. So the fact that you guys are kind of ripping out the Solana virtual machine, that you can like rewrite, like a lot of this is not dependent on like the actual Solana layer 1 implementation, because you guys are kind of going to adapt things to your own implementation.
Yeah, so I think some of the on-chain smart contract work can be reused with the Solana L1, but we're not actually depending on the Solana L1. We do plan on using like Solana as one data availability source if apps prefer that, but they're definitely not locked into using that.
So like how far you would like so you said that you need to implement like 4 proofs to IBC. Like how far are you along with it, or like what's your thinking there?
So I'm still sort of working on like a draft of like what changes we could make to the protocol. I think we're gonna start with the simpler, like wait the entire challenge period before delivering messages, because that helps us get like an MVP like ready. But I think that isn't ideal. So still trying to draft the like exact details of how that could look within the protocol. Like maybe like we tag all the messages with like some bit saying like we're delivering the message, but it's not yet settled, and then we deliver like another bit like further down the line, where we say like this message has actually passed the entire challenge period, something like that. Still trying to work out the exact details of that right now.
Okay.
Modular Joe asking. Okay. Modular Joe is asking, so you're planning to commit to the SVM state every block by using a Merkle tree? Yep, that's correct. And actually, IBC like has some built-in spec for these things called vector proofs. So what they're essentially like doing is you can commit to sort of the Merkle root, and then a specific member of this Merkle tree with like a much more sparse representation of all the nodes. I believe it's like the entire path of nodes from the Merkle root down to the specific node that you care about. So like it typically only requires log of n space. So yeah, we are planning to do that. I think it's pretty standard for like other chains as well. So like